Today, I'll be presenting interactive streaming infra with JupyterHub and Apache Flink on Kubernetes. And the main motivation of this talk is streaming in general is tough, but we'll describe how with building and providing it as a managed service and how providing interactive streaming might help you to adopt streaming within your company and make it way easier for your customers, basically. I'll share how you can build streaming platform and scale it up using only like open source software. It's Apache Flink or Kubernetes or JupyterHub. And all these opinions are mainly of mine and doesn't represent my company. So here's our agenda today. As I mentioned, like streaming is tough. So at first we'll start with challenges, like learning challenges, like how it is different from batch. And then we'll talk about infrastructure and language challenges. The goal is not to discourage you, but actually to understand these challenges. And then I'll provide potential solutions, how you can eliminate these challenges. And then we'll go how you can build streaming infrastructure on Kubernetes. And then we'll start from single pod deployments, start small and let the users use it, and then actually how you can scale it at big data scale. So the first steep learning curve is about bounded versus unbounded data, like batch and data processing for big data was there for a while, but actually streaming is relatively new. So it takes some time for users to do a mind shift. So how to apply processing on like unbounded data, or they need to learn new time characteristics. Is it event time processing or like wall clock time? Or how do you handle out-of-order data or late arrival data? So solution for alleviating all these kind of challenges is you need to provide tons of examples. Like it can be tons of Flink SQL examples or PyFlink examples. Like I really like Flink SQL cookbook on GitHub repo provided by Ververka, where it provides like concise, small Flink SQL examples where you can actually copy paste it and then see what it does. And so too many important things are needed. So for the playground where the users can just log in and start using it, so they can get hands dirty and then they can tweak few parts and understand. And then you should make like controllable random data generation super easy for them to get started. Because in streaming you will do mostly like joins, and then it's better to have like easy way to generate actually controllable random data. So the next challenge is actually connector-specific knowledge for Kafka and Iceberg commits. And then I'll mainly touch base Kafka and Iceberg because these are the most widely used connectors in streaming world. So the first thing with Kafka, like even though you're just running Flink or you want to run just Flink, you still need to touch base few other distributed systems. So like if you're using Kafka, most probably you will need to touch base with schema registry, and then your users need to understand how the schema evolution will work. Or for Kafka, let's say if you have empty partition, how do you make sure your Flink job actually doesn't stall? Like specifying idle timeout for your partitions, or how do you actually know how many partitions you need to have for your Kafka topic, or how do you make sure like you don't have disbalanced partitions? Or for Iceberg, you need to understand how Iceberg commits work, or when the data is actually gets committed, or when the metadata is getting committed, or how Iceberg table size can impact your job manager memory size. Like all this kind of like nitty-gritty details, like in addition to Flink itself, you need to know connector-specific knowledge. Usually, open source documentation would not be that great. There are many ways to specify these configs, and some of them work or some of them doesn't work. So like potential solution to this going and actually improving like open source documentation or having internal documentations in your like data platform, or you build your own SDK, you wrap the like good defaults for your customers, and there are only like tens of common mistakes where your customers can make. So you can actually specify those default configs and save your customers some time for that. So the next challenge is actually about there are too many knobs for Flink. If you compare to Spark, there are many memory tuning or like how many task loss you need to have. And Flink memory config, actually, there are maybe at least 6, 7 different components of memory you need to tune, and like network buffers, like off-heap memory or Java heap space, and lots of other components. So it's actually challenging, even for experienced like streaming engineers, to tune it. So then, even if let's say you started with Flink Java, which is the most stable and which is the most powerful one, but then some of the users might be using PyFlink. So then scaling of PyFlink pipeline would be actually different than scaling your Java pipeline, because Python processes are involved there. Or let's say if you're using Flink SQL, it would be different, because users write pipeline in Flink SQL, and then it automatically is converted to Flink job graph, where you don't know beforehand what kind of operators will there be. So the only option you have is actually you can specify, if you're lucky, like sync or source parallelism, but for the rest you will just specify the job level parallelism, which is common for all your operators. Then here, Flink Kubernetes Autoscaler, like several teams, including my team at Apple, has contributed and built and contributed back to open source Flink Kubernetes Autoscaler, and also Flink Kubernetes Operator can come and help you actually. So what this does, basically it helps you to not babysit your pipeline. It will automatically upscale or downscale your pipeline based on the data volume you receive. And starting actually 1.8, it can not only tune your parallelism, but also tune your memory, except managed memory, which is usually reserved for your RocksDB. So check that out starting Flink 1.8, Flink Kubernetes Operator 1.8 version. And it does work seamlessly in Kafka source, and lots of companies are using it in production. And Iceberg source was also recently contributed back to open source actually. Now we'll switch gears into infrastructure challenges. So usually when you have like streaming pipelines and then you want to run it on clouds, like on Kubernetes, then there might be different pod failures or task failures. Flink have like job manager, which is master node, and then Flink will have several task managers, which are worker nodes. So here, like, so I'm talking about the failures not caused by the user, like faulty code, but actually infra-related failures here. So let's say the node is unhealthy, or your DevOps team is doing some cluster maintenance, or like due to several reasons, your job manager or task manager can fail. So if you enable in your Flink Kubernetes Operator can help again. If you enable HA mode, high availability mode for your job manager, then that can handle it like gracefully. And then basically you can save your jobs depending on your job graph. It can save your whole job, like not to restart basically. And task manager failures can be handled easily by Flink Kubernetes Operator, so you don't need to be paged for any like single pod failures. The next challenge is actually, again, this is another reason like why running streaming on clouds is tough. You might be hit by object storage limit. You might be hit by this in two scenarios. First is when you have, let's say per operator, more than 1,000 parallelism, and then you have really large checkpoints. Or you're actually, let's say, writing into Iceberg, and then all your data are going to the same bucket. And then you might be faced, like, for some object storage, like it's 3,500 puts only per second, and then your pipeline will start, like your checkpoints will start failing. And then the solution for this is you need to cooperate actually with the vendors. And you need to tell them, at first you need to enable entropy for your pipeline. For Flink side and then Iceberg side you can also do, but then you also need to cooperate with like object storage vendor providers by telling them, okay, what your path will look like and where this entropy hash will be injected. So they need to manually extra repartition say buckets. So it can handle extra amount of the load, not to cause you like to hit that limit basically. The next challenge is, again, this is another reason why streaming is hard and it might be really expensive. Let's say your user needs to know, or your infra teams at least need to know what cloud providers are charging for their different services. If you co-locate your Kafka and Flink clusters in the same availability zone, then you can save like tons of network costs. If you still have Kafka clusters in different zones, then you might actually have separate pipelines running, and then you can broadcast your single topics in both regions, and then do joins in each availability zone separately. That might be one solution to save network costs. Now we'll talk about language challenges, and here I mean by programming languages used by different user categories. So let's say you have built your streaming platform, you started with Java, and you got all your Java savvy, like data engineer teams, like onboarded, but then you need to grow your platform and you need to acquire new customers the next target might be like machine learning and data science people. But they usually only either know like Python really well, or they can write complex SQL queries, but they don't know Java. They would be good with Scala usually, but Flink doesn't mingle well like with Scala wells, as the Scala support is not as good as Java one. So then your only option is actually like Python or SQL support going forward to get those customers. So, and if you support, then basically to accommodate this natural organic requirement from your customers, you need to provide 3 APIs of Flink, like both Java, Flink SQL, and PyFlink basically. Flink provides a layered API with Flink SQL and PyFlink on the top, and they are mainly different from other layers because of ease of use, and they still keep the flexibility of the same expressiveness almost. So for streaming analytics and ML use cases, Flink SQL and PyFlink are the most recommended one, and this is what the rest of the part of this talk will describe basically. We recommend building managed service around Flink SQL and PyFlink and provide it for interactive streaming, and then using it for streaming analytics and ML use cases. So of course, if you have like Java savvy users, they can always opt for a Java API, and they get the most features out of Flink, and but with added complexity. So Flink SQL is the easiest API to build. You just write in pure SQL, and then it gets automatically converted to Flink Job Graph. And then Flink SQL is based on ANSI standard SQL, so you actually don't need to learn new SQL, but it's almost same SQL as you're used in like your relational databases, or it just have few extra things like temporal operators or watermark, or like a few minor things which you can learn. And then it eliminates the requirements of being Java or Scala developer, basically. So with Flink SQL and then with UDF support, where you can write your UDFs in multiple languages, including Java, Scala, or Python, you can actually accommodate most of the use cases, and like maybe 70% of all the use cases can be handled with this. So then for interactivity or for easy of use, the second one is PyFlink. Actually, PyFlink might be a good fit for ML framework integrations, such as PyTorch. Let's say you have machine learning models implemented in PyTorch, and you want to generate inferences at scale and then ingest it to like Lakehouse. Then you can use PyFlink basically, and it supports table and data stream API. And another reason I like PyFlink, in Flink SQL, it's very easy to get started, but it's super hard actually to write tests. But with PyFlink, you can write your tests like way easier and test your end-to-end logic basically using like unit tests or integration tests basically. And PyFlink nicely integrates with Pandas, one of the most widely used Python model, which you can use with your PyFlink also. So far, I have presented challenges, but the goal is not scare you. Now we'll talk how we enabled interactive streaming development. First, we'll start with single pod deployment, what we used, how to put it into clouds, and then we will shift gears to talk how to do it actually at large scale. So Flink open source comes already with Flink SQL client, which you can use as a like as an interface for your users to get started. And then most of the Python users are used to, or machine learning people are used to Python notebooks, or so they can continue using like Python notebooks. So we decided to build actually streaming support on top of these two APIs mainly. So the first challenge when we wanted to build was, okay, we don't want the users to build anything in their local laptops, which is super challenging to set up. So what we wanted to do is, so they just need internet connection and they need web browser to get started. And then one of the options was JupyterHub. So our sister team was already providing JupyterHub like as a service on Kubernetes, so we just decided to reuse it. We mainly use it to put actually shell, like terminal literally on the cloud, so users can access it, like with authentication and everything already provided. And then users are already familiar with JupyterHub Workspace UI, so they know how to use notebooks, they know how to use terminals, and then for each Jupyter lab image, basically they can create multiple sessions, and then there's EBS volume attached to each like session. So basically any notebook you create there or any user code you write there will stay alive even if your notebook is shut down after several hours of inactivity. So it's pleasant experience, and you can integrate it with GitHub. You can easily check out, clone your repo, and do everything on Jupyter Lab basically, and you don't need to do any setup like in your laptop basically. So in order to achieve this, what we did, we baked Flink open source into a Jupyter Lab image. And then whenever user goes and starts session, Flink local cluster will be started in that Jupyter Lab. And this Flink local cluster will then be able to talk to different, like Kafka running on different EKS cluster, or it can publish your metrics actually to different metrics DBs you support, and then it can read write into like Iceberg tables. And the user just like opens the terminal and then starts Flink SQL client, and then they can start writing it. It was good enough to get started with single pod Jupyter Lab and running small enough cluster with maybe 10, 20 task slots. And users were happy using it because Flink jobs usually are not as memory hungry as like Spark. So it was good enough to get started. But soon we started getting the limitations of like single pod. The main reason is that once the user actually started to using Iceberg source a lot, then for Iceberg table size actually determines how much memory you need to allocate to your job manager. So job manager, it's not like linearly dependent, but it is like heavily dependent on your input Iceberg table size. So then you needed more resources, but single Jupyter Lab pod like will have limitation on CPU and memory, and like you cannot cover all the use cases, specifically machine learning use cases where you want to, let's say you need a GPU, but usually Jupyter Lab pod will not run on instance types which supports GPU enabled. So for those kind of use cases then we needed to change our design, and then we suggest like we build it and contribute it back to open source, how to enable basically remote execution for Flink pipelines, basically building Flink SQL and building via Flink SQL and PyFlink. You build it still on Jupyter Lab, like using Flink SQL client or in IPython notebooks, but actually your jobs are running on separate EKS cluster. So from now on, now we'll focus on talking first how to build this on Kubernetes. So it's more like technical deep dive now. And if you'll have, I'm sure you'll have many questions, so then I can answer like in office hours, like because this will be too technical. And so let's start. So what you see here is the user on the left side, and let's say they are on JupyterHub, and then we see two Kubernetes clusters. So control plane is nothing like more than, let's say it's a web app with a Kubernetes client, which can, and then you usually want to deploy one control plane for, let's say, your cloud provider account, and then you might have actually many Flink EKS clusters, and like multiple of them. And then in each cluster, you need to have Flink Kubernetes operator deployed, which will manage end-to-end lifecycle of your Flink pipelines. So the first step, the user needs to submit some kind of deployment JSON-net or like YAML file, basically, to control plane and to start the session cluster. So this interactive development is actually based on session cluster usage. And then I'll explain like how proxy servlet like will be used in the next. So user submits the creating session cluster request, and then this request is at first like it hits the proxy servlet and it gets authenticates the request. Okay, this user actually is authenticated to run this, and then it passes it to control plane, which will authorize this user. Can this user actually create session cluster on this namespace in Kubernetes? Once all the checks are passed, then it creates custom resource and submits it to Flink Kubernetes operator. Then Flink Kubernetes operator will start a Flink session cluster where you see like job manager is started, and then you can determine if you want task managers to be started at the same time or actually let them started whenever there's a query submitted. You also see SQL gateway within job manager pod. There are two ways to run it, either within the same pod or you can run it as a side container depending like how many users will be using it. And then once SQL gateway, which is just another Java process, started in job manager, it's ready to start receiving SQL queries to be executed. But the whole communication, there need to be connectivity between these two EKS clusters. So, and that is handled by a control plane. Whenever it creates this session cluster, in addition to Flink custom resource to create this session cluster, it also creates service and ingress. And this ingress is not globally available. It's only actually available to this control plane cluster, and all the user communications goes through this control plane via proxy servlet, basically. So user only needs to know the Flink UI link, which will be proxied through the control plane, and all the interaction will happen through that. This is end-to-end flow. So let's say you have already started your session cluster, and then user starts issuing commands. They can write in Flink SQL client, or they can actually submit the whole file to this. And when they start the SQL client, they need to specify endpoint URL of this Flink UI. So your SQL client actually connects to remote session cluster. And then the query gets through proxy servlet. Again, authentication, authorization will happen. Then it will be forwarded to ingress, and then that will make its way to Flink SQL gateway, which will compile and generate a Flink job graph for you, and then submit it actually to job manager. And once the results are ready, then job manager will stream the results back to SQL client. One good thing, like up to Flink 1.8, Flink Kubernetes operator did not support scaling up your session clusters, but now it supports. So you can just start small, and based on like a natural growth of your users using this kind of interactive Flink SQL, then your cluster can be scaled up. And you can have one cluster per user, or a single cluster can be used by many users, basically. Now we'll switch to PyFlink interactive development workflow, which is the second one. This is mainly for machine learning users, or if you want to get like more expressiveness. Let's say if you want to use key process functions or some low-level APIs of Flink, which you cannot do in Flink SQL, or you want to write actually extra tests for your pipelines, then you can switch to PyFlink. So this starts similar here. First thing you need to do is actually create standalone like session cluster. And for that one, in JupyterHub, we ship a control plane client, we also provide REST API for our control plane. Basically, you deploy your JSON net, which will start as a session cluster for you. And then before that, again, authentication and authorization is handled in control plane. So once it is validated, then it will get the Flink CRD, and it will be directly submitted to Flink Kubernetes operator, which will start your job manager and task manager. So the only difference between this and Flink SQL gateway is you don't have, Flink SQL interactive way, there is no Flink SQL gateway here. So you just work, control plane directly talks now to job manager, basically. once your session cluster is started, then the next step for user is just start PyFlink, like writing your PyFlink job, and you can do it inside your IPython notebook. The only thing you will need is, again, the endpoint URL of your Flink UI, which you will specify via environment variable in your IPython notebook, and then you don't need to set up anything else, basically. Flink Python will underneath handle the whole communication and everything. So once you, let's say you wrote your PyFlink pipeline in IPython notebook cell, and then you press execute the cell, then the Python code is converted actually into a Flink job graph inside this on the JupyterLab terminal side, which is different from the Flink SQL, where Flink SQL gateway was converting it on the cluster side to job graph. But here in this case, your job graph is created on the client side, and then it gets submitted to control plane, and then control plane will actually forward it to Flink like job manager. So your pipeline will start running your Flink pipeline, and then once your results are ready or your results are streaming back, depending on which mode you're using, you will see in your IPython notebook already is results of your Flink pipeline. That's it of the presentation.